Now let's turn this airplane. We're going to come back. So what we're going to do, we've pushed it out at 70.7% of the speed of light. Now we're going to turn it around and push it back. So here he comes back this way in space. And so what's going to happen in time? Let's draw these vectors again. So the airplane number 2 has gone this way in time. Airplane number 1 has gone that way, rotated his frame of reference, so time is that way, space is that way. And now he's going to turn and come back. What has happened? Okay, when he turns and comes back, airplane number 2 is going to be right about there. So remember, in the original scenario, as airplane number 1 went out, he had to look over his right shoulder and behind to see airplane number 2. But when he turned, now airplane number 2 is in front of him. So here, airplane 2 is falling behind in time, falling behind in time. He turns and suddenly airplane number 2 is ahead in time. So just like in the spatial scenario we just showed, when airplane number 1 turned around, airplane number 2 swung around in space to become ahead of him in space. Now airplane number 1 turns around and he sees airplane number 2 go from behind him in time to ahead of him in time. So he has jumped from one frame of reference where airplane number 2 is behind to a new frame of reference where airplane 2 is ahead. And now he's going to travel back there. And remember what's happening, we're just pushing him back towards it. So they're both going through time at the same speed. I push one out and push him back. He's gone through space and that's caused this geometry. And when he gets back, he can never catch up. So however far this has gone through time, I'm not going to put any numbers here, but as we see now, this one has fallen behind in time to now, whatever time this one has gone, let's say 2 years, I don't know, whatever it is, been pushing them for a long time. This one, although he's also gone 2 years through his own time, in airplane number 2's time, he has only gone 1.414 years. Now we've got a bit of a problem here because he's fallen behind in time, but actually this clock seems like it should have ticked off the same amount of time. So what's going on here? There's still something not quite working. And that's because to make this work fully, we have to throw in length contraction into the calculation. Oh. So remember that when we turned in the three-dimensional space, the perspective changed so that the airplane was only 70.7% as long as it was from that point of view. But we know it's really the same length. Well, when we throw in space as a fourth dimension, remember we have the two planes. Now when he measures in his dimension, he finds that he is only 70.7% the same. He has become shorter in space. So he sees in space a smaller airplane. But of course, the observer in airplane number 1 sees the same thing. He sees that his wings are actually 100 meters, where he takes that over to here. He sees that this plane only takes up 70.7 meters. So each observer sees the other one length contracted. So when you see something moving, it appears length contracted. When you are moving through space, you feel like you're stationary and you see space moving by you. Well, if you see something moving, shouldn't it be length contracted? Yes. Space itself becomes length contracted. So that enters into the equation to finish off what actually happens. So here's our airplanes. Once again, if they're stationary, they're going through time, but if we push one, it's going through both time and space, and we get the anomalies we just saw. Let's say that we send this airplane off to a target that is 90 million kilometers away. So here we go. Airplane number 2. Airplane number 1, he's going to go off 90 million kilometers at 0.707 c. So 0.707 times the speed of light. Now remember, he feels stationary, but he sees space going by him. So that means that space will actually be length contracted. That's one thing that most people don't get about length contraction. It's not contraction of objects, it's the contraction of space itself. So from his frame of reference, as space goes by, space is length contracted. So from airplane 1's frame of reference, that distance is only about 63.6. 63,600,000 kilometers. So he sees that as a shorter distance. So he speeds off, traveling through time at the same speed of time as everyone else, and sees himself traveling at 0.707 times the speed of light. Therefore, the distance he goes is going to be contracted to 70.7% of the original. So he's going to see the time it takes to go at 70.7% of the speed of light to his destination, which is now only 63.6 million kilometers away, is going to take 3.54 minutes. However, airplane number 2 is still traveling this direction through time and not through space. And if he could see airplane number 1 arrive at the destination, he would see that in his time, that took 5 minutes. So there's a disagreement in the two clocks. So why is the disagreement? Because not only does he see him traveling slower through time, but the observer in airplane number 1 sees space contracted, so it takes him less time to reach the destination because it has become closer. So he sees that he's reached a destination in 5 minutes, if he could see it, where his clock says, oh no, I reached that destination in only 3.54 minutes. Now we're going to turn around and push him back, and he's going to come back over, and it's going to be the same distance, another 3.54 minutes, for a total of 7.07 minutes, where, of course, airplane number 2 has traveled through time for a total of 10 minutes. So when airplane number 1 comes back, airplane number 2 is going to say, ah, your trip took you 10 minutes. But airplane number 1 is going to say, not so. It only took me 7.07 minutes. So we see now that when we add length contraction in, that the clock in airplane number 1 is actually going to tick off less time because of length contraction. He's going less distance, even though he's going at the same speed through time. So he goes out and comes back, and the two clocks disagree. So what have we seen here? We have seen that if we take time as a fourth dimension with the same characteristics as the dimensions of space, that when something travels in space relative to us, it will go through less time than we do, and the other person will see us as the one traveling, so it'll see us going through less time. But as he goes out here to his destination, that airplane number 2 sees as 90 million kilometers, because he's going through space, he feels stationary, so it looks like space is going past him. Therefore, space is length contracted, as I showed before. The length space is going to become length contracted, so his distance becomes shorter. Therefore, he takes less time. And when he turns around, he finds at his turning point, what happens? Airplane number 2, that had been falling behind in time, is suddenly ahead in time. So he goes from one frame of reference where airplane number 2 is behind to a new frame of reference where airplane 2 is ahead, and he can never catch up. And when we get back together, they compare clocks. And since airplane number 2 went through less space because of length contraction, his clock went through less time. Therefore, airplane number 1 went through less time than airplane number 2, and their clocks disagree by about 2.9 minutes. So we see that using the simple Euclidean geometry, it might be a little confusing at first, but we do see that, oh, if we have two objects going the same speed in the same direction, they appear to be motionless. But if one goes through a different dimension, it's going to lose ground in the other. We switch this over to time. We see that if one airplane stays stationary and the other one moves, one's moving through time only, the other one's moving through space and time. Therefore, it's losing ground in the time dimension, according to this observer, but he sees that the other one is losing ground in the time dimension because he's rotated his frame of reference. So we take the two analogies and put them together. We find that when something travels relative to you in space, it must fall behind in time. And that goes for both observers. But The one that goes out and turns around suddenly goes from one frame of reference where the other object is behind in time to a new frame of reference where the object is now ahead in time and can never catch up. And because of length contraction, that moving object went through less space than the other one will perceive, and so he ticks off less time because he went less distance, going the same speed, and so when they get back, their clocks will not agree. So what have we solved here? We've solved time dilation and length contraction. We've also solved the twins paradox. So what's the twins paradox say? The twins paradox says that we have two twins, exactly the same age. They're both on Earth. And one decides to take a trip to some distant space. We usually use Alpha Centauri as our destination. It's something like 4.3 light years. And so one twin goes out to Alpha Centauri and comes back. And when the one going to Alpha Centauri gets back, he's younger than the twin who stayed on Earth. How can this be? Well, special relativity says that when one twin is going out, he's going to be going slower through time compared to the first one. But the one that's moving is going to see the observer on Earth going slower through time. So theoretically, when the traveling twin gets back, each one is younger than the other. And that's the paradox. But we just showed that that isn't a paradox because when this observer turns around, he goes from a frame of reference where the other twin at the Earth is behind him in time to a new frame of reference where the observer on Earth is ahead of him in time. So it's the changing of the frame of references that reconciles the clocks so that when the traveling twin gets back, he actually is younger. Now, some say that this happens because the traveling twin accelerates. And that's true. Accelerating rotates your frame of reference in space-time. And so that's exactly what happens. Other observers say that, well, you don't need any acceleration. Let's say that there's already somebody coming back the other way, and just when the traveling twin gets to the destination, the second traveler passes by, and they synchronize their clocks when they travel by. When the second twin arrives, he's going to be behind just like the first, so no acceleration required. Well, the acceleration simply changed the frame of reference. The second traveler is already on the frame of reference that the twin on Earth is ahead of him in time. So that works either way. So you can explain that in a number of ways, but the important thing is turning around, changing direction through space-time rotates the frame of reference, and that's why the traveling twin ends up younger than the stationary twin.